The newly born universe buzzed and frothed with boundless energy. Even after the raging furnace of the first few minutes had died away, temperatures universe-wide were more than 100 million degrees. For thousands of years, this primal heat burned a cosmos of plasma, a superhot mix of particles and radiation. Until, one day, it changed forever. That day arrived when the universe was almost 400,000 years old and had cooled to about 3,000 Kelvin. In this now comparatively tepid soup, lone electrons met lone protons and finally could stick together, forming the first atoms. But this was not all, for as each electron and proton bound together, a small amount of energy was released. A packet of energy that raced away at the cosmic speed limit, the speed of light. A particle of energy born in the formation of a hydrogen atom. A particle we call a photon. A particle of light itself. This photon was far from the first, but as the universe began transitioning from plasma into neutral gas, light could then, for the first time, stream freely through its reaches. And so, our photon's long journey began. It headed out first into the universe's dark ages, a time before the first stars burned, a time before the first galaxies formed. In the eerie darkness, gravity pulled on mass to mold the first seeds of cosmic structure. But the photon sped on and noticed nothing. Eventually, the first stars burst into life around it. Massive and bloated, these ancient suns burned themselves out in a cosmic blink of an eye as the first supergiant black holes grew rapidly between them as they eagerly devoured mass. But the photon sped on and noticed nothing. The first galaxies began to assemble. The sky lit up with the fires of uncountable young stars across the cosmos as they began to fuse the initial hydrogen and helium atoms into heavier elements. But the photon sped on and noticed nothing. Millions steadily turned into billions of years, and as galaxies grew and matured, eventually the intense light of young stars began to settle. The photon's journey could have potentially lasted forever into eternity, but after almost 14 billion light-years of travel, a large spiral galaxy steadily came into view. Its destiny was set. Near a small blue dot orbiting a small white star, after crossing the last few thousand light-years, the photon collided with a piece of metal, part of a telescope built by humans and orbiting near the planet Earth. The photon's energy was completely absorbed, energizing electrons and registering on detectors. But as the photon vanished from existence, its billions-year-long journey complete, it still simply did not notice. Because, to the photon itself, the journey never took place. 13.8 billion years of cosmic time disappeared in an instant. Yet how can this be? Light has existed in the universe from its earliest moments and will continue to exist long after humanity and the stars are shred to dust. But just how does it work, and how can it seemingly last forever? And perhaps most importantly, what even is it? Light is fast. It only takes 0.13 seconds for it to circulate the entire globe. Through fiber optic cables, that slows down by a third, but that still means that with Surfshark, changing your virtual location is almost instantaneous. Surfshark have been kind enough to sponsor this video, and they are the best, simplest VPN service out there. You can change your country quickly and easily to stream whatever you want from wherever you want in the world, with more than 100 countries to choose from. Light seems to escape definition as it exhibits properties of both a particle and a wave. And now you too can be similarly inscrutable to big tech companies and cybercriminals by using Surfshark to mask your IP address and encrypting your data on public Wi-Fi. It's the best way to secure your personal information when using the internet and even warns you of potential data breaches. So check out Surfshark by clicking on the link in the description and get 83% off and 3 months for free, as well as a 30-day money-back guarantee. Thanks to Surfshark for supporting educational content on YouTube. Light had played a pivotal role since the cosmos's very beginning. In these earlier times, it had only existed for the very briefest of moments, slamming into speeding particles before it had a chance to travel anywhere, one piece of light dying as another was born. However, our parcel of light was born into a very different, very transparent universe. With the cosmic maelstrom of the Big Bang finally abated, our photon could begin its immense journey unhindered. As it travelled, many generations of stars led to our sun, and billions of years after, humans began to walk on the surface of our small, rocky planet. And so eventually, as our photon was a couple of thousand light years distant from Earth, those humans began to wander. All men by nature desire to know. An indication of this is the delight we take in our senses, and above all others, the sense of sight. This, most of all the senses, makes us know and brings to light many differences between things. The ancient Greeks wondered if light emanated from the eyes, touching and feeling the world around us. But clearly there are times when it is dark, when we can't see anything. So they concluded light must be something external, something captured by our eyes. Islamic scientists went on to unravel the properties of light, finding rules of reflection and the magnification properties of glass lenses. Light was clearly a natural part of the universe around us. But it took the coming of the scientific revolution and a fight between two giants of science for light's deepest secrets to be finally uncovered. The year was 1652, and Dutch physicist, astronomer, mathematician, and all-round genius Christian Huygens was exploring optical phenomena. He had noted how light travelled through lenses and bounced off mirrored surfaces, and was particularly interested in the phenomenon of refraction, where the path of light is bent when it passes from one medium to another. Huygens noticed that light was often split into the colours of the rainbow by his instruments, and sometimes strange patterns of dark and light would be produced. Clear evidence to him that light was some sort of wave, some sort of travelling, oscillating phenomenon. Oscillations can be found throughout nature, from planetary orbits to vibrating electrons. But let's start with a simple picture. Think of a child on a swing. As they swing, their position oscillates from one position to the next and then back again, just like a pendulum that drives the regular ticking and tocking of a grandfather clock. When oscillations act in unison but slightly out of step, waves are formed. A stone thrown in a flat pond pulls the water down with it, but the water bounces back. This splash of water pulls on its neighbours, inducing them to oscillate, which in turn pulls on their own neighbours. These oscillations fan out across the pond as a steadily rippling pattern of waves. Waves are everywhere, from sound waves coursing in the air to ocean water waves driven by the wind and moon. Seismic shifts can generate violent and destructive earthquakes in our planetary crust, whilst similar waves ripple in the atmosphere of the sun and other stars. And so, light seemed also to be a wave. But this left an obvious question. If light is a wave, just what was doing the waving? In Britain, Robert Hooke also reached a similar conclusion about the nature of light, and he realized that this picture of wavy light could explain a lot of the phenomenon he had seen. This was cutting-edge science at the time, but Hooke had a problem, and that problem was a man. There are no surviving portraits of Robert Hooke, and over the years a rumour passed down the generations that this powerful man was to blame, having conveniently lost the painting when taking over as head of the Royal Society in London. For Robert Hooke had a powerful enemy, and that enemy's name was Isaac Newton. Since cleared of any wrongdoing in the absence of contemporary images of Hooke, there is still little question that the two men were not friends. For as well as his far-reaching discoveries in mathematics and gravity, Newton also had an interest in optics and the nature of light itself, and he did not like what Hooke or Huygens had to say. Indeed, it was Newton who discovered that white light could be split into a rainbow by passing it through a prism, and like Hooke, he had kept musing on this. But unlike Hooke, Newton did not conclude that light was some sort of wave. To Newton, light consisted of corpuscles. To Newton, light was made of tiny, individual particles. Newton's focus was the phenomenon of diffraction, the fact that waves bend around a sharp edge. He knew that sound, a wave in the air, bent as it travelled past sharp edges. It was clear that you could eavesdrop on a conversation from around a corner without being able to see the gossipers. You could hear from behind an object, but you could not see. So, he reasoned, light simply could not be a wave. And he didn't stop there. Newton went further. Much, much further. He reasoned that light, as a stream of particles, would even feel the pull of gravity. In his book Optics, published in 1704, he wrote, "Do not bodies act upon light at a distance, and by their action bend its rays?" And though on this he was correct, he was not proved correct for centuries. So it was Newton's corpuscular theory of light that reigned supreme, due more to his weight of personality and scientific standing as opposed to its ability to explain the complex observations of light. Over the years, however, steadily the tide began to turn away from Newton. In 1800, polymath Thomas Young shone light through a pair of narrow slits and observed a pattern of interference on a background screen. This wasn't the first demonstration of interference, but it was the clearest. How could Newton's picture of light as particles explain Young's observation of interference? How could light, as tiny bullets passing through either one slit or the other, produce the observed pattern? Simply throwing a couple of pebbles into a still pond reveals that interference is naturally produced by waves, either in water or in light. Other observations of light supported its wave-like nature, including light's polarization through a material called calcite. But for centuries, the big secondary question remained unanswered. If light was a wave, just what was doing the waving? Our cosmic parcel of light was born when a proton captured an electron. It sped out into the universe powerful and energetic. But as it travelled and the universe expanded, it started to lose some of that energy. The light, originally blue to our eyes, steadily morphed through the colours of the rainbow and into the red. Soon it was joined by other energetic light shining from countless billions of newly formed stars. There were different types of light as well, light of exceptionally high energy and light with barely any energy at all. The universe was awash. Of course, our light did not know that these would be invisible to human eyes, for it would be many billions of years until eyes existed. And indeed, these X-rays and radio waves, as we call them, were unknown to us until the very end of the 19th century. In this new era, thought itself will be transmitted by radio. Guglielmo Marconi was at his father's estate near Bologna in Italy. He was still a young man, aged only 20, but his education had opened his eyes to an invisible world. In the decades before, the nature of light had steadily been unraveled, and Marconi was ready to use this newfound knowledge to change everything. Staring at his equipment, Marconi was waiting to see a faint spark in the darkness. With the bundle of wires and coils of his workshop, such a spark would not be surprising. But the impetus for this spark was not in the equipment before him, it was in similar equipment located several miles away. Of course, the 19th century had seen the arrival of the telegraph, where electronic pulses were sent along wires that crossed entire countries and continents. But this needed wires to be strung through the air and under the oceans. Marconi had no need for such wires. He would be sending messages not along bits of copper. His messages would simply fly, completely unseen, through the air. But how? The answer lies with one of science's greatest geniuses. The answer lies with James Clerk Maxwell. When a young James Clerk Maxwell arrived at the University of Cambridge in 1850, he was told that attendance at the 6 a.m. church service was compulsory for all students. The Scottish-born prodigy had long been a night owl and simply responded, "Aye, I suppose I could stay up that late." His name is writ large across the modern world, but his crowning achievement was uniting two seemingly disparate phenomena and creating something remarkable. Electricity and magnetism had been known about since ancient times, seen in the strange attraction of rubbed materials and mysterious stones that knew how to find north. But by the 19th century, it was becoming clear that these two were not truly distinct. A flow of an electric current could generate a magnetic field, and a changing magnetic field could generate a current in a wire. But as Maxwell stared at these equations, he began to see a deeper picture. Instead of separate relationships, he saw that electricity and magnetism could be united into a single whole, a united set of mathematics that encompassed all electric and all magnetic phenomena. But Maxwell's great insight was not only concerned with electromagnetic complexity, for he wondered about the simplest situation of all: electromagnetism in the nothingness of a vacuum. How does light travel through the emptiness of space? Maxwell knew that electromagnetic fields filled all of space, even in vacuums, but it was imagined that in empty space these fields would be null, effectively not there. But what if you plucked one of these fields, either electric or magnetic, so that these fields were not at zero at some location? Maxwell pondered this question, using his equations to explore how the situation would evolve. And the answer was astounding. Think about pinching the skin on the back of your hand. What happens when you let go of your pinch? Your skin sinks back to its unpinched self, quickly if you are young and somewhat slower if you are older. Maxwell's equations told him that the electromagnetic pinch would evolve away back to zero, but that this was not the end of the story. Pinching the electric field would generate a similar pinch in the magnetic field, and the pinch in the magnetic field would generate a pinch in the electric field. And these pinches did not simply fade back to zero. Instead, they oscillated, regenerating each other from one moment to the next. And just like ripples on a pond, these oscillations traveled away as waves. And so Maxwell realized these oscillations had the property of light. Light, he realized, is a self-propagating electromagnetic wave. But what was causing the ripples? What was the electromagnetic equivalent of the stone thrown in the pond? He saw that it was electric charges, something we now know as electrons. As these charges jiggle and oscillate, they disturb nearby electric and magnetic fields, and these disturbances ripple away as electromagnetic radiation, what we call light. He also realized that the inverse must be true, as light entered the eye and fell on the retina. The oscillations of the light must cause electrons in atoms in the eye to jiggle, and it is this jiggling of electrons in the eye sent as signals to the brain that we perceive as vision. Finally, Maxwell understood what it was that was waving, and what caused the waves. And one more thing. He knew that light had waves with a length of about 1/1,000,000th of a meter, but his equations showed no limitation on the wavelength of his electromagnetic waves. and so he concluded that there must be light with both long and short wavelengths that is invisible to the eye. It would take 2 more decades for the answer to this puzzle to present itself, decades in which Maxwell died of cancer at the age of only 48. In 1886, Heinrich Hertz, working at the University of Karlsruhe, was the first to find these invisible waves. Named Hertzian waves after their discoverer, a new revolution had been born. We now refer to these Hertzian waves as radio. Hertz was understandably very pleased with his discovery, but when asked about the practical use these radio waves have, he apparently responded, "Nothing, I guess." And yet, it was these radio waves that only a few years later Marconi was using to send messages across miles, and then across counties, oceans, and all across the immensity of the globe. In 1909, Marconi received the Nobel Prize for his work on wireless telegraphy. Hertz, however, died in 1894 at the youthful age of 36, never seeing the true promise of his discovery. The world was set to become full of invisible light as the 20th century began, and the mystery of light's properties seemed settled. That was until 1905, and a remarkable year for one German patent clerk. The universe continued to change and evolve as our particle of light traveled. The mixture of light joining it on its journey reflected that change, bursts of radio waves and high-energy gamma rays becoming more and more frequent. This energy surged through space, much of it flowing between the stars and into the darkness. But some encountered lone atoms in the emptiness of the void. The low-energy radio waves very gently shook and energized these atoms, like a calm ocean wave lapping at a sandy shore, just as we would expect from Maxwell's picture of electromagnetic waves. But the behavior of the high-energy gamma rays was different. They delivered their energy to the atoms with a violent punch that ripped electrons clean away, not a lapping ripple, but an isolated smash. The gamma rays hit the atoms not like waves, but like hard, little, energetic particles. But how? Could Maxwell be wrong? Could, on some occasions, light be more like Newton's vision and act like a particle? And if so, just what would those occasions be? For the present, we have to work on both theories. On Mondays, Wednesdays, and Fridays, we use the wave theory. On Tuesdays, Thursdays, and Saturdays, we think in streams of flying energy quanta, or corpuscles. Alfred Nobel had made his fortune through his inventions and his businesses, especially in the field of explosives and weapons. And so, perhaps not unfairly, in an 1888 obituary in a French newspaper, he was called the Merchant of Death. This surprised Nobel, firstly as he was still very much alive, but secondly, and more distressingly, because he realized what his historical legacy was to be. So, in his will, he decided to leave most of his fortune to a series of prizes that would honor those that have conferred the greatest benefit to humankind. Across science, the Nobel Prizes are perhaps the most prestigious, the list of winners replete with the giants of science over more than a century. And in 1901, the inaugural Nobel Prize in Physics was awarded to the German Wilhelm Röntgen for his discoveries about the nature of light. For it was he who discovered the X-ray. Röntgen's experiments with various materials found that only the densest could halt X-rays. He even managed to convince his wife, Bertha, to place her hand in the beam, after realizing his X-rays should stream through her flesh, but be partly blocked by her denser bones, thus producing the first X-ray photograph. Whilst it was suspected that X-rays were electromagnetic radiation with a wavelength much smaller than visible light, as opposed to radar, which was much longer, it took several decades to conclusively show that this was the case, although in the meantime the medical application of X-rays to fix bones and save lives grew without bounds. And so this meant that by the early 1900s, Maxwell's vision of electromagnetic waves beyond the visible had been undoubtedly confirmed, all of light's secrets uncovered, even the electron having been discovered. All that remained was to find the rest of the light we could not see, gamma rays, microwaves and more, to fill out the last gaps on the electromagnetic spectrum and wrap up the story. But of course, if physics feels that a job is done, a rude shock is usually just around the corner. In Maxwell's picture of light, it could be thought of as a continuous wave. Scientists had found that when light crashed into most materials, it continuously dumped energy that energized electrons, causing them to be emitted. This was called the photoelectric effect. By lowering the intensity of light, it took longer for energy to be deposited, and it usually took longer for the electrons to begin to be spat out. Usually. For that was not what was observed when light was shone on certain metals. Electrons would seemingly be ejected instantaneously from the metal's surface, and the really confusing observation came from adjusting the color of the light being shone. Blue light would result in very energetic electrons being emitted. Green light resulted in less energetic electrons, and red light produced no electrons at all. This made no sense. If all colors of light carry energy, why did red light fail to energize the electrons? This mystery was solved and new mysteries were born in a very special year. This was no ordinary year, it was a miraculous year, for it was the year that Albert Einstein changed physics forever. Most people are familiar with Einstein's Annus Mirabilis, 1905, the year he wrote down the special theory of relativity. But that was just the beginning. Einstein was awarded the Nobel Prize in Physics in 1921. The citation noted the award was for his services to theoretical physics. Yet one topic in particular was singled out for recognition, and it was not his work on relativity. It was especially for his discovery of the law of the photoelectric effect. When Einstein explored the photoelectric effect, he had to radically revise Maxwell's vision of light. He realized that when light interacted with electrons, it could not do so as a continuous wave of energy. Instead, the energy must be concentrated and dumped into an electron as an instantaneous packet. Light, Einstein declared, must be quantized. It must be chunks of energy. It must interact like a particle. Einstein went on to explain that each packet of energy was proportional to the frequency of the light. A packet of red light carries less energy than a packet of green light. A packet of green light carries less energy than a packet of blue, and so in experiments, the red light simply didn't deliver enough energy for an electron to escape. This enigmatic packet of energy didn't get its current name until 1926, when in an article in the journal Nature, Gilbert Lewis coined the name photon. Evidence for the particle nature of light swiftly grew, and it was in 1923 Arthur Compton put together an important experiment, but one that relied on a bizarre fact. Light can push. This might seem like a strange thing to say. How can light, which has no mass, push? But Maxwell's equations showed that, in carrying energy, light also carries momentum. You can easily buy a Crookes radiometer today as an executive toy for your desk, consisting of 4 vanes in an evacuated glass tube, one side black and the other side white. When placed in bright sunlight, the vanes begin to spin, pushed, supposedly, by the momentum of nothing more than sunlight. As ever, the physics of the Crookes radiometer is more complex than this simple explanation, but the force of sunlight pushing on the vanes is real, with some visionaries imagining future humanity coursing amongst the planets, solar sailing on sunlight. In 1923, Arthur Compton's experiment, however, was a little different. In his experiment, Compton aimed a beam of high-energy X-rays at an atomic target, thus ripping electrons from the outer part of the atoms. But when examining the rebounding X-rays and recoiling electrons, Compton found that Maxwell's picture of a wave of energy and momentum simply did not work. Instead, Compton had to treat the X-rays and electrons like colliding billiard balls. For when an X-ray hit an electron, it delivered its energy and its momentum as a discrete packet. When an X-ray hit an electron, they definitively interacted like hard particles. Newton's vision of particles of light was reborn. But was this definitive proof that light was a particle? Not quite. There was, of course, still a mountain of evidence for its wave-like nature. If anything, scientists were more confused than ever before. Despite Maxwell's picture of electromagnetic waves proving extremely powerful and successful, these experiments in the early 1900s demanded that light must be a particle. And so people began to wonder, was there even an answer to be found? We began this story following a photon of light as it traveled across the universe. Maxwell tells us that this photon was formed by the changing energy of an electron, and that it vanishes when finally absorbed by electrons at its journey's end. But what happens in between? Is this epic journey simply governed by fate? Does the photon really fly off in a random direction, careening into an electron at some arbitrary point in its future? This question is the next part of our story. For in the early 20th century, it was realized that this simply could not be the case. In the language of quantum mechanics, the photon's journey has nothing to do with chance. Not only is the universe stranger than we think, it is stranger than we can think. We begin on a chilly morning in France in January 1793. With the swish of a guillotine blade, the king, Louis XVI, was no more. Throughout this upheaval, chaos reigned across France. Victor Francois, the second Duc de Broglie, battled for his king, but eventually, like many others of the aristocracy, he fled France for safety abroad. The de Broglies eventually returned to their native France to shape the country after the upheaval of revolution, and after a series of statesmen, diplomats and writers, in 1892, into the de Broglie family was born the man who would change our understanding of everything. His name was Louis Victor Pierre Raymond, 7th Duc de Broglie, but in the annals of physics history, he is simply known as de Broglie. In the early 20th century, he bore witness to the birth of quantum mechanics and a growing confusion about whether light was a particle or a wave. To de Broglie, however, there was one obvious solution, though a counterintuitive one. Light was neither and both at the same time. It was clear that light, when it travelled as a wave, producing the effects of interference and diffraction. But when it interacted like a particle. It seemed to exhibit properties of being both a particle and a wave, but was never really either. De Broglie's remarkable insight was to realize that this was true not only for light, but for the entire quantum world. Here, he claimed, there were no true particles and no true waves. Everything, de Broglie told us, was some sort of quantum thing. And so, in his PhD in 1924, he claimed that electrons, which were clearly particles, should also exhibit wave-like properties. And in 1929, he received the Nobel Prize when experiments bore out his predictions. There has been significant philosophical discussion about this wave-particle duality in quantum mechanics. but its observational consequences are incontrovertible. A series of single photons or electrons sent through multiple slits still result in interference patterns, and even large, complex molecules have also been shown to have properties of both waves and particles, the largest yet tested being 2,000 atoms in size. And so, with quantum mechanics in hand, the quest was on to understand just how light and electrons interacted. With classical physics, the physics of Maxwell, electrons jiggled as electromagnetic waves passed by, just like seagulls bobbing on a choppy ocean, and by their jiggling, the electrons emitted their own electromagnetic waves, adding to the mix. But the quantum picture had to be different, for the quantum world was one of quanta and particle reactions. Despite these opposing situations, it didn't take long for a solution to be found, and it was another scientific titan, Paul Adrian Maurice Dirac, that began to crack the code. In the late 1920s, he was working to unite two of the greatest breakthroughs in modern physics: the strange world of quantum mechanics and Einstein's special theory of relativity. Dirac's story has been told many times about his famous absent-mindedness and lack of communication skills. Quantum pioneer Niels Bohr went as far as to call him the strangest man. But there is absolutely no doubt that Dirac was a revolutionary genius, and it was through his work on quantum mechanics that Dirac made his mark on scientific history. To understand the modern view he helped to bring about, we have to accept that everything is actually fields. These fields are different to things like classical electric and magnetic fields. In quantum field theory, there are electron fields, photon fields, fields for the various quarks, and more. A ripple, for example, in the electron field is an electron, and a ripple in the photon field, a photon. Think of an atom. What do you see? In our minds, we often have the picture given to us by Niels Bohr of electrons orbiting a nucleus like a planet orbiting a star, and when an electron jumps from a higher orbit to a lower orbit, a photon of light is emitted. But when considering the quantum world, this is not quite correct. In quantum field theory, we think of an orbiting electron as a vibrational pattern in the electron field. The higher energy orbit is one particular pattern, and the lower energy orbit is another. In the language of physics, the electron field and the photon field are coupled together, and jumping between the higher and lower orbits, the electron field generates a vibration in the photon field. Quantum field theory has grown to become arguably the most successful theory of our world to date, describing almost everything in our universe across 24 quantum fields, corresponding to the various possible interactions of the standard model. And so, simple. Everything is fields, and the fields interact. But, of course, as they often do in the quantum world, things are about to get a lot stranger. Many of the greatest minds of quantum mechanics were involved in this move towards strangeness, but perhaps the most well-known is a man from Far Rockaway with a broad Brooklyn accent. A man named Richard Feynman. Born in 1918, he started his career as part of the Manhattan Project and was recommended by Oppenheimer himself for Berkeley in a now famous letter sent in 1942. He is by all odds the most brilliant young physicist here, and everyone knows this. I may give you two quotations from men with whom he has worked. Bethe has said that he would rather lose any two other men than Feynman from this present job, and Wigner said he is a second Dirac, only this time human. Though his 1985 autobiography, Surely You're Joking, Mr. Feynman, was an eye-opener for many, not only regarding his numerous contributions to science, but also his extroverted personality and complex private life, including a penchant for strip clubs. These aspects did not fit the stereotypical vision of a professor. Indeed, Murray Gell-Mann, another giant of quantum mechanics, once even quipped of Feynman, Feynman was a great scientist, but he spent a great deal of his effort generating anecdotes about himself. And yet, when it came to thinking about the quantum world, for many physicists, Feynman changed everything. Whilst Feynman's famous quip that no one truly understands quantum mechanics may have been true, Feynman himself certainly understood the depth of the mathematics that underlies it. And this gave him the insights to think about the true nature of light and how it interacts. It all starts with a solitary electron. In the electromagnetics of Maxwell, the charge of the electron results in an electric field surrounding it, and a charge in an electric field feels the presence of the electric field. In this situation, there must be energy in the interaction, but the question was, how much? The problem was, every time Feynman tried to calculate the amount of energy, the answer came out to be the same: infinity. So, Feynman did something quite radical. He threw away the classical notion of the electric field as defined by Maxwell. In the acceptance speech for the award of his Nobel Prize in 1965, Feynman said, "I suggested to myself that electrons cannot act on themselves, they can only act on other electrons." And a new, bizarre picture of the interaction of light and electrons emerged. The best visual representation of this interaction is the diagram named after Feynman himself, the Feynman diagram. They are often a complicated mixture of lines, wiggles, and loops, but at their heart, Feynman diagrams describe all of the possible interactions in quantum mechanics. To pick apart a Feynman diagram, it is best to start with the simplest of interactions, the interaction between electrons and light. Feynman diagrams represent an interaction over space and time. Lone electrons trace out straight-line paths through space-time, a path known as its world line. The electron is really just a vibration in the quantum electron field, and with no interactions, it happily traces a simple straight-line path. We also know, however, that the electron field can couple with the photon field, and when this happens, the vibrations in the electron field change. In an atom, the electron jumps from a high-energy orbit to a low-energy orbit. But for a free electron, conservation of momentum means that the electron changes direction. If we imagine this over space-time, the world line of the electron possesses a distinct kink, and this occurs where and when the photon, usually depicted as a wavy line, is emitted. This structure, this junction, is known as a vertex, and it is the basic Lego piece for building all Feynman diagrams. Of course, full Feynman diagrams are more complex than a single vertex. They usually combine several distinct pieces. The emitted photon from one electron is eventually received by another electron. Two vertices are joined together to give the complete interaction. Two kinked electron paths joined with the wiggly line representing the photon. But what governs the coupling between the electron field and the photon field? This is related to the charge on the electron and one of nature's constants, the fine structure constant. This is electromagnetism, and the exchange of the photon between two electrons is the electromagnetic force in action. And so, in Feynman's view, we wave goodbye to the electromagnetic field. In its place, we simply have two electrons interacting through the exchange of a photon, and when huge numbers of these photons are exchanged, it approximates the classical force, even though, at its heart, this electromagnetic force is a quantum phenomenon. And it's not just electromagnetism, for it is also true for the fundamental weak and strong nuclear forces. For the strong force, it is gluons instead of photons that are exchanged between quarks. And for the weak force, it is via the exchange of massive particles known as the W and Z. And again, all of these forces can be presented by a combination of Feynman vertices. But this was not the end. Feynman had one even stranger card yet to play when it came to light. He had said that one electron acts upon another, and this happens through the exchange of a photon, producing the complete Feynman diagram of the interaction. But did this mean that an electron fired out a photon at random? Did this photon stream out into the universe with only a remote chance of being absorbed by another electron? Counterintuitively, the answer, Feynman said, was no. He told us that the photon is only passed between two electrons that have agreed on the exchange. But there is something odd happening here. If we are in the middle of the photon's journey, its emission from one electron occurred in the past, while the absorption of the photon by the other electron is going to occur in the future. So when did the electrons communicate and agree to exchange the photon? How did they even know of each other's presence? It clearly cannot be via the electromagnetic force, as this is precisely what the exchange of the photon actually is. So, what is the solution? As with a lot of quantum mechanics, whilst the mathematics just works, the interpretation, the question of what is really happening, is the biggest challenge. And so Feynman, with his supervisor John Wheeler, put a mind-bending possibility on the table. The suggestion is something we now call the transactional interpretation. They said that the two electrons handshake their acceptance of exchanging the photon, but that this handshake is taken through time. One electron messages from the past, and the other from the future. This might sound ridiculous, but it completely fits with the mathematics of quantum mechanics. And so, on a dark night when you gaze at a distant star, an electron in your eye and an electron in the atmosphere of that star spoke to each other through time and agreed to exchange the photon you see. And going even further, for the lonely photon we met at the beginning of our story, two distant electrons shook hands over billions of years of time, billions of light years of space, and agreed that the photon should undertake its cosmic journey. The bizarre world of quantum mechanics never disappoints. And yet, there is one final, even stranger mystery to unfold about light and our lonely photon in the blackness of space. As it travels over many billions of light years, just what does the photon experience? We've followed our photon over many billions of years. Eventually, at journey's end, the universe it inhabits is very different to the one of its birth. Yet there is a disconnect. For whilst this photon was almost as old as the universe itself, it remained eternally youthful. Galaxies formed in the void, stars were born, lived and died, whole superclusters splintered and collapsed. And the photon missed it all, because, to the photon, time itself meant nothing. This might seem like a strange thing to say. The photon clearly had an existence in time, but with the coming of Einstein and his special theory of relativity, it was realized that time was actually flexible. It was relative, dependent upon who or what was actually measuring it. And light takes this idea to the extreme. What would the universe look like if I were riding on the end of a light beam at the speed of light? In the middle of the 17th century, Ole Romer was baffled. Working at the Paris Observatory, Romer was peering at Io, one of the bright moons of Jupiter. Like clockwork, the moon orbited the giant planet in just over 42 hours, vanishing from view as it ducked in and out of Jupiter's shadow. Except there seemed to be something odd about this cosmic clock. Romer noticed that the timing of Io's eclipses drifted. He realized that the timing of the eclipse of Io was somehow tied to the Earth's orbit, changing from earlier to later and back again when the Earth was either closest to or further from Jupiter. And it was then Romer realized the culprit was light, and in particular, its speed. He reasoned that the drift in Io's eclipses must be due to a finite speed of light. As the Earth moved in its orbit, the distance to Jupiter changed, and the change in time was because light had to traverse these differing distances. His initial estimate for the speed was fast, very fast, 220,000 kilometers every second, and eventually more accurate measurements tied the speed of light to almost 300,000 kilometers per second. But just what was this speed relative to? It had been the belief for centuries that there existed a medium, the ether, that carried light waves. Surely, therefore, light speed was relative to this medium. From Plato to Newton, this ether had long been suggested as a solution to various questions in physics, but never firmly detected, experiments in search of evidence having failed time and time again. And so it was that in 1905, during his miracle year, Einstein rang the final death knell for this invisible medium: special relativity. The truth was that it was the speed of light that was the universal absolute and invariant, measured to be the same value for all observers across the cosmos. A lot has been written about special relativity, and although much of it seems confused and paradoxical, there is a simple central message at its heart. Particles with mass, such as electrons, chart out their own time as they travel through space-time. Imagine two clocks sitting at the same location, synced to show exactly the same time. Now take these clocks on two separate journeys, speeding them up and slowing them down. In Newton's view of the universe of absolute time, if you were to bring these clocks together again and compare their faces, they would have remained synchronized. But this is not the case in Einstein's. The relative motion of the two clocks will have influenced their relative passage of time, and as they trace out their different paths through space-time, when they reunite, their times will now be out of sync. This mind-bending aspect of relativity seems too strange to be true, but numerous experiments have shown this to be the way the universe works. From globe-trotting atomic clocks to high-speed particles in accelerators, time is definitively relative. But what does this mean for light? Light had taken a central place in Einstein's new vision of the cosmos. Everyone in space-time should measure the speed of light to be precisely the same value. But in demanding this, something else had to give. And so, space and time themselves had to bend, become flexible and rubbery to accommodate the consistency of the speed of light. Indeed, one immediate consequence of Einstein's insights was that light would feel the existence of gravity, and as it traveled through the universe, light's path would be deflected by the presence of mass. Newton's claim of 2 centuries prior, reborn. Indeed, experiments have borne this out again and again, with the results becoming more and more accurate. Massive objects, such as stars and galaxies, can even behave as gravitational lenses, magnifying distant galaxies from the very early universe and revealing the presence of dark matter. The beauty of these natural telescopes is clearest in deep space images, such as the first revealed by the James Webb Space Telescope. And so, the flexible nature of space and time had truly seen the end of Newton's view of a rigid universe. But again, what about light? What did this mean for light's experience of space and time? Traveling at the fastest speed possible in the universe, the effects of relativity become extreme, very extreme. All distances shrink to zero, as does the time taken to cover these zero distances. And so, for photons, no matter how far they travel across the universe, not a single instant of time will tick by. Even though this light may have existed in time and space for many years or light years, even though it would have been clearly formed by one electron in one location and vanished when absorbed by another electron in another location, the space-time distance between these two events would be exactly zero. To the photon, it is born and dies at precisely the same moment. We began this story by following a lone photon from its creation just after the beginning of time to its ultimate destruction in the detector of a telescope orbiting our planet today. And yet, the photon itself saw nothing of this. Not the intense light of stellar birth, the catastrophic explosions that come with stellar death, or the formation of planets and eventual rise of life on our own pale blue dot. The photon noticed nothing. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.